In the first part of this course, we analyze the RC circuit, which uses a capacitor. We learn the equations that model the behavior of this capacitor, and we use them in order to understand how the RC circuit behaves. Now, in this lesson, we will expand our knowledge by incorporating models of capacitors and inductors. We will also learn how to apply these models in conjunction with the analysis methods that we already learned. For a capacitor, we learned that there are two equivalent equations to describe its behavior. The first one describes the current, and it is a differential equation. The second version is used to describe the voltage, and it is an integral equation. The equations for the inductors are very similar to the capacitor equations. If you take a closer look, you will see that the equation for the voltage of an inductor looks just like the capacitor equation for the current, but the terms current and voltage are swapped. Similarly, the equation for the voltage of a capacitor has the same shape as the current for the inductor. These equations can help us understand how inductors work. From the current equation, we can see that the inductor is a component that accumulates current, while the capacitor accumulates voltage. The second equation tells us that the voltage at the terminals of an inductor depends on the change of the current that flows through it. If there is a fast change of the current, the voltage will be high. One analogy that can help us understand inductors is thinking that the inductor is like a road where electrons in the shape of tiny cars flow. When these tiny cars are pushed into the inductor, they will have some energy and they will try to continue moving across it. Real inductors are built as follows. There is a wire or a conductor that is wound around a magnetic material. The magnetic material can be in the shape of a stick, like in the picture, but it can also be in the shape of a toroid or a ring. In the kind of circuits I built, inductors are not frequently used, but for some applications, like power converters, they are one of the main components. Continuing with the analysis methods, let's start by determining the formulas to calculate capacitors and inductors connected in parallel and series. When we have two capacitors connected in parallel, like in this diagram, we can see that there is a current represented by the symbol I that enters into the two capacitors C1 and C2. This current is split into the currents I1 and I2. Since the two capacitors are in parallel, the voltage across their terminals is the same, and it is represented by the symbol V. From this diagram, we can derive the first equation that tells us that the current I is the sum of I1 and I2. We can replace the equations that we know for the current of the capacitor, and we will obtain the second equation, which shows the derivative of the voltage, but with two different coefficients, C1 and C2. After simplifying this equation, we can see that it looks just like the original equation for the current of the capacitor, but it has the sum of the two capacitance values. From this last result, we can conclude that when two capacitors are connected in parallel, they form an equivalent and bigger capacitor. The capacitance value of the equivalent component is the sum of the two capacitors. Let's perform a similar analysis, but now for capacitors in series. In this case, a current I flows through both capacitors, but the voltage V is shared by each capacitor. V is the sum of voltages V1 and V2 corresponding to each capacitor. In this equation, we can replace the model for the capacitor, which is an integral, and after simplification, the equation can be written as follows. Here the highlight is the term that sums the reciprocal of the values of each capacitor. That's the equivalent capacitance. We can conclude that the equivalent capacitance of two capacitors in series is the reciprocal of the sum of the reciprocal values of each capacitor. And because of that, two capacitors connected in series result on a smaller equivalent capacitor. One interesting thing is that this formula looks like the formula to calculate two resistors in parallel. If you remember, The equations for the inductors look very similar to the capacitor equations, but with the symbols V and I swapped. If we follow the same analysis using the inductor model, we reach to the following formulas. Connecting two inductors in series results in a larger inductor, which is the sum of the two individual inductors, while connecting them in parallel results on a smaller inductor. In the case of capacitors, connecting two in parallel makes a larger capacitor. Let's continue with an example where we will analyze a circuit which combines capacitors and inductors. This circuit is called RLC because it has one resistor, one capacitor, and one inductor. If we look at the diagram of the circuit, you will notice that it has a single loop. Therefore, it will be easier to analyze using mesh analysis. We start by writing the loop equation, which is the sum of all the voltages in the loop. We have the input voltage minus V1, followed by the voltage of the resistor R1, then the voltage of the capacitor C1, and last the voltage of the inductor L1. In the next step, we replace the voltages by the corresponding component model. You can see that we have an equation where one term is an integral and the other one is a derivative. If you remember your calculus lessons, we can apply the derivative to each term of the equation in order to cancel this integral. In this case, minus V1 becomes 0 because it is a constant. For R1, it results in the derivative of the current. The integral gets cancelled, and in the case of the inductor, which already contains the derivative of the current, it results on a second order derivative. If the last step was a bit difficult to follow for you, I will show you a very easy way of doing it using Wolfram Language. Here, I have written the equation in Wolfram Language. The main thing to notice is that the current is not constant, therefore it changes as time passes. In that case, it is written as follows. Here you can see how we write the integral, and here you can see the derivative. In the output, we can see the equation with the integral symbol. The notation uses a backtick to represent the derivative. We assign this equation to the variable EQ1. If we want to apply the derivative to the whole equation, we can do this as follows. We can see that this is the same result that we have seen before, but uses the backtick notation for the derivative. This is a second order equation, and these kind of equations have been widely studied. But before going deeper into the analysis of this equation, let's run a few simulations to have an idea of the behavior of this circuit. With this line of code, I will run a set of simulations where I change the values of the capacitor and inductor. The values are not arbitrary. I have picked these values in order to illustrate the following result. Here are the plots of the current in the circuit for different capacitor and inductor values. We can see that the current increases and then makes a few oscillations until the current is stable around 0 amperes. But the blue result is the one that has the higher initial peak, but it is also the one that gets stable sooner. The red result is the one with the lowest peak, but also the one that oscillates longer. Let's see the second set of simulations. With these specific values, all the peaks are the same level, but what changes is the frequency of the oscillation. This is very intriguing. Let's find out how I selected the values of the components. Here you can see again the equation we obtained for the RLC circuit. Next to it, there is the general form of a second order system. As I mentioned before, this type of systems have been characterized, so their behavior is known. We can see that it is possible to match the terms of the two equations. By making the following replacements, we can convert the RLC equation into the general second order equation. 2 times alpha is equal to R1 over L1, which is this term, and omega 0 squared is equals to 1 over C1 L1, and that is this term. The two parameters omega 0 and alpha define the behavior of the system. Omega 0 is the natural frequency, which defines the frequency at which the system oscillates. That's the parameter I changed when creating this plot. Alpha is the damping ratio. but when designing a system, it is more useful to use the symbol zeta, which is defined as the damping ratio over the natural frequency. I obtained the second plot by changing the damping value represented by zeta. In order to get the component values for a given natural frequency and damping, we need to take the equations that we defined that convert the RLC equation into the general second order equation. Here you can see them. We can replace the value of alpha in the first equation in order to express the formulas in terms of zeta. Then we can solve the resulting two equations in order to obtain C1 and L1. Since we are one equation short, we need to provide the value of R1. Here I have a simulation that calculates the values of capacitor and inductor for the input natural frequency and damping. The value of R1 is set to be 1 ohm. As I change the parameter omega 0, we can see how the frequency changes without changing the peak. When changing zeta, we can see that as it approaches to 0, it starts oscillating more and more. If we increase it, we can notice that any value above 1 does not oscillate, and it increases a little bit the peak, and this settling time becomes longer. Let's go back to zeta equals to 1. This is an important value. It is called the critical damping. This value has the characteristic that it does not oscillate, and it has the lowest peak and also the fastest settling time. To summarize this lesson, we learned that capacitors and inductors are modeled using differential equations. We derived the formulas for parallel and series connections of capacitors and determined that for inductors, the formulas are swapped. We learned that the RLC circuit results in a second-order system. These kind of systems have been characterized, and we derived the formulas to design the circuit according to the parameters we wanted.